Now I introduce optimal baselines for reinforcement method. We have introduced the likelihood ratio trick before. By using the likelihood ratio trick, we can simplify the gradient of the objective function from a complicated integral to expectation. It means sampling summation. So it's another advantage from the likelihood ratio trick is here. Originally we need to calculate the derivative of the object function. Now we just need to calculate the derivative of the policy pi. And using this relationship, we can find use the this likelihood ratio method to separate the policy calculation from the state transition probability. That means when we search for the optimal policy, we only calculate the derivative of the policy. We don't need to include this environment or this state transition probability into the gradient. That's true because when a human, for example, we use the demonstration to train the model. When human at this state, and how can we select the policy? So the human have to first we check what's the environment, and then we select the proper policy to get the maximum reward. Here in the reinforcement learning, agent follow the same way. When the agent try to search for the best policy, it has to be to first check or investigate, or from the training example, try to fully understand how the human make their decision in this dynamic environment. So that's why here we separate the policy from the environment. But however, if right now we change the integral to the expectation, also we all need to think about two problems. One is the bias, one is the variance. It's caused by the how can we sample the problem. Right now, because the problem, we sample is along a trajectory. So we don't need to worry about the bias because the bias is zero. This procedure is unbiased. However, if we sample along a trajectory, we will have a big variance. Right now, in this topic, we are introduce the baseline to reduce this variance. For example, if we sample along a trajectory, so the mean of the samples is same as the original mean for the or true distribution. But we sample along the trajectory, we will have so many points, we will have a variance problem. Sure, we have so many examples. When each example we have a different variance. That's why later we calculate the baselines for each example. Make sure we get for the expectation we have a minimum variance for all the examples in the training data set. So if we check the formula, this pi this probability distribution and is a gradient, and use the ratio trick, and here use this this equal 1 because it is all the possibility. So it's equal 1, so equal 0. That means we can insert any number in this gradient of the objective function. Because this term is 0, so we don't, no matter what's b we select, it doesn't affect the gradient of the objective function. So we have a chance to select a proper baseline to reduce the variance. To do so, suppose for each example, is the variance defined as this sigma, and to reduce the variance for each example, we should make sure this original gradient of the objective function here is his expectation formulation. Make sure they are same. This is just a minimal problem with the constraint, and this uses this equation. So finally, because right now we just use the baseline for each example in the training data set. Finally, we just use this Janssen formulation. We just make each make the variance for each example or element is minimal. So we just get this formula and get this formulation and calculate his derivative. And then we got about with respect to b, and then we got a baseline for each element. And we insert this b we got included in the gradient calculation, and then we got the unbiased and the minimum variance. For more details, please check with this reference. Thank you. Bye.